Hi, my name is Ping Shi, and I'm an assistant professor at the University of Southern California. It's my joy to be able to present to you my research at this workshop. The title of the paper is Optimal Priority-Based Allocation Mechanisms. In situations in which monetary transfers are limited, scarce items are often allocated by priorities, including seats at public schools, units of subsidized housing, as well as cadaver organs. This paper is about optimizing over these priority-based allocation mechanisms. The challenge here is that the policymaker does not know how much each agent values each kind of item. So this is fundamentally a mechanism design problem. And it is a difficult mechanism design problem because there are many different kinds of items. Moreover, there can be institutional constraints on what priorities can or cannot depend upon. Here's an outline of the talk. I'll first overview the background and the contributions, then discuss the model, the results, and I will conclude with a discussion on practice-driven research in keeping with the theme of this workshop. My broader research agenda is designing optimal systems for matching students to public schools, applicants to subsidized housing, customers to service providers, as well as in other socially important contexts. This paper will be focused on matching students to public schools. Here are the steps in pursuing this research agenda. First, we want to document the existing inefficiencies, then obtain a theoretical understanding. Third, we want to obtain implementable prescriptions, which we lastly test in field experiments. I've done many of these steps in the past. In this paper, we'll be focused on refining the theoretical understanding as well as obtaining implementable prescription. Here's some background on public school choice. In many cities, based on student characteristics such as where they live, where their siblings go to school, as well as possible test scores, students receive individualized menus. So this is the set of schools they're eligible for. And out of this set, they indicate their preferences. And oftentimes this is a ranking. So my top choice, second choice, third choice, and so on. Schools also prioritize students based on their student characteristics, such as where they live. Moreover, school board decide on the capacities of each school. And so these items in yellow, the menus, priorities, and capacities are controlled by the school board. And these are policy levers. And the preferences, priorities, and capacities are fed into a certain assignment mechanism which determines the school assignment. Such a system is implemented in many cities around the US, as well as around the world. So previous works have focused on this assignment mechanism. My research is focused on these inputs, the menus, priorities, and the capacities. And let me talk about the deferred acceptance mechanism, which has many desirable theoretical properties and is widely implemented. So the inputs here are the preference rankings of students, the priorities, as well as capacities. And inside the computer, each student applies to their top choice, and the school tentatively accepts. But when capacity is violated, the school will bump out the least priority student, and that student will apply to their next choice. And this keeps on iterating until each student is either assigned or has gone through their entire preference ranking and have been bumped out everywhere. To illustrate, suppose there are two schools, A and B, each with unit capacity. And Bob applies first to his top choice, school A, and is tentatively accepted. Alice also likes school A and applies. At this point, the capacity of school A is exceeded. And here, in this example, Alice has higher priority. So Bob is bumped out and applies to his next choice, school B, and is tentatively accepted. Let me remind you that in order to implement such a mechanism, the needed inputs are the menus, what schools each student is eligible for, the priorities, which decide who gets bumped out, as well as the capacities at each school. And the research questions in this paper is first, coming up with the optimal design of these inputs, the menus, priorities, and capacities for the deferred acceptance mechanism. Second, it will be comparing deferred acceptance with alternatives such as top trading cycles while accounting for the flexibility of these inputs. Here are the contributions of this paper. First, I illustrate that restricting choice may maximize utilitarian welfare. So reducing the size of the menus may be beneficial to students. Second, I characterize outcomes achievable using deferred acceptance and top trading cycles when these inputs, the priorities, can depend on a given set of agent characteristics. So this helps us to compare what these mechanisms can do under flexible inputs. Third, I give efficient algorithms to compute the optimal menus, priorities, and capacities for deferred acceptance under many objective functions and preference distributions. And lastly, I apply the framework to real data from Boston to compute near optimal menus and priorities for elementary school assignment. And this is motivated by the 2013 Boston school assignment reform, which I will describe later. Let me briefly overview the relationship to literature. This paper contributes to the growing literature on optimization in matching markets. There are previous works on the design of priority distributions, but they focus on comparing a few possible options, such as deferred acceptance with single tiebreakers or multiple tiebreakers. On the other hand, I optimize over a large set of priority distributions. There are papers related with implementing priorities and quotas to achieve certain outcomes, but they tend to take these priorities as given, whereas I'm going to take these as decision variables. In terms of techniques, this paper builds on large market models of one-sided matching, as well as techniques from assortment optimization. Let me go over the model. I'll first talk about the features of the model and then the details. Here are the features of the model. The policymaker can decide what characteristics can be used to differentiate agents. For example, for school choice, policymakers may decide home location is possible to determine menus and priorities, but race and gender cannot be used. And based on this decision, policymakers classify agents into segments, and the model will guarantee that those from the same segment will receive equal opportunities from an ex ante perspective. Second, this model allows flexible assignment mechanisms, as the mechanism can be any function that maps actions and priorities into assignments. This allows it to encapsulate deferred acceptance, top trading cycles, and other commonly implemented mechanisms. Here are the details of the model. For tractability, I consider a large market framework with continuum of agents. So a unit mass of infinitesimal agents coming from one of these M segments designated by the policymaker are to be matched to one of N items. Lambda T is the proportion of agents of segment T, and Cj is the capacity of item J. Agents receive certain utility vectors, which specifies their cardinal utility for each of these N items plus one outside option. And this N plus one dimensional vector is drawn according to a distribution F, which may depend on the segment. A priority-based allocation mechanism is given by a set A of actions a set pi of possible priorities, a distribution G, which may depend on the segment, determining the priorities. So each agent of segment T will have his or her priorities drawn according to this distribution GT. And an allocation function X is a mapping from action and priority to item. Based on such a mechanism, each agent is assigned to a certain item X of A star pi, where A star is the agent's chosen action. This is the action that maximizes his or her utility given this allocation function X. You can interpret this as each agent knows their own priorities when choosing the action and chooses the best action that maximizes utilities. Even if agents don't know their priorities, this can be satisfied if the mechanism satisfies certain strategy proofness properties in which the optimal action does not depend on the priority pi. And this property is satisfied by both deferred acceptance as well as top trading cycles. Let me go over the results. There are 4 results corresponding to the 4 contributions I discussed earlier. The first is the potential benefits of restricting choice. Here, I'll give 2 stylized examples to illustrate why reducing menus may be helpful for students. Take an example in which there are 2 neighborhoods, each with a highly desirable school. So school 1 is in neighborhood 1, school 2 is in neighborhood 2. Here are some assumptions on the utilities of students. So U of 0 is the utility of a student for their neighborhood school. U of 1 is for the other school. And alpha is for their outside option, which may be other schools in the district with excess capacity, as well as possible private options. The result says that neighborhood-only assignment maximizes utilitarian welfare among all priority-based allocation mechanisms if the following condition holds. So the left-hand side here is the expected value of U0 minus alpha conditional on U0 greater than equal to alpha. Think of this as the benefit to a neighborhood applicant. On the right-hand side, this is a similar expression where U0 is replaced with the maximum of U0 and U1. Think of it as what happens when we open up enrollment. So each student is picking their favorite school, and the applicants are those who likes one of these schools better than their outside option. U0 minus alpha is always less than equal to the maximum of U0 and U1 minus alpha. This conditioning makes it so that the left-hand side may indeed be larger. For example, if people's preferences for their neighborhood school are either high or low, and the preferences for the other school, U1, is between H and alpha. In this case, the neighborhood applicants, which are those who have a high preference for their own school, will receive a higher benefit from being assigned than these choice-induced competitors, which are people who have a low benefit for their neighborhood school, but if you open up enrollment, they will apply to the other school. In this example, restricting choice is beneficial because the neighborhood applicants on average derive higher benefits than the choice-induced competitors. Here's another example with possibly many neighborhoods of different sizes, as long as the ratio between school capacity and neighborhood size is fixed across these neighborhoods. And in this example, you don't need asymmetry across neighborhoods. So this utility of each student for any school is drawn according to the same distribution F. And the result is that neighborhood-only assignment maximizes utilitarian welfare among all priority-based allocation mechanisms if the outside option distribution H has a heavy left tail. What this means is that most people have okay outside options, but a few people have bad outside options. So here, restricting choice is beneficial because it leads to a more efficient allocation of outside options. if you open up enrollment and allow people to apply to any school in any neighborhood, there may be people who have okay outside options who are now induced to compete for seats. And they would displace certain students which need those schools more because they have very bad outside options. The next result is a comparison of DA with alternatives, given that these inputs, the menus, the priorities, and the capacities can be flexible. The theorem says that for certain priorities and capacities, deferred acceptance can implement anything that can be implemented by any priority-based allocation mechanism. And deferred acceptance with single tiebreaker, which is a refinement of DA, already encapsulates top trading cycles as well as serial dictatorship. And top trading cycles is the same as serial dictatorship when we consider these flexible inputs. And serial dictatorship is one where we order students by priorities and have each student picks their favorite school among those remaining. And this characterization helps us see that if we have flexible inputs, deferred acceptance is all we need. And the proof also constructs the corresponding priorities and capacities to implement various outcomes. And this helps us because once we can compute the allocation we want, we can use the proof to back out how to implement it. Next question is, can we efficiently compute these optimal priorities as well as capacities? And the answer is yes, under certain conditions, as long as we can solve this key sub-problem in which we want to find a certain set S, so a certain set of items that balances the utility of students from a certain neighborhood as well as the externality they impose on others. And the theorem is that this optimization can be solved for the following parameters, including multinomial logit utilities, as well as cardinality constraints on the set S. A more complex D-level nested logit utility model. A two-level nested logit model with certain types of cardinality constraints, as well as these Markov chain-based choice models, which are designed to be approximations of any random utility model. In this paper, I'll be applying the multinomial logit utilities and cardinality constraints. The multinomial logit model is estimated from past student preferences and indicate how much each student from each neighborhood likes each school. And the cardinality constraints will help us limit the transportation cost of the city. Let me go into more detail by discussing the empirical application, which is based on the 2013 Boston reform, in which the policymakers wanted to find the best menus and priorities that depend on home locations in order to balance busing requirements, expected utilities of students, as well as the predictability of the system. So here, capacities are treated as fixed, but in the paper I show how one can use heuristics to handle this discrepancy from the previous framework. Let me give some examples of menus and priorities. So before the 2013 reform, Boston used the 3-zone assignment plan, which partitioned the city into 3 geographic zones. So here, the menu of a student, the set of eligible schools, are any school within their zone of residence, as well as a 1-mile radius around their home. There are also additional priorities for those living within the 1 mile, which apply only to half of the seats in order to allow people outside the 1 mile to have a chance. After the reform, policymakers chose this home-based plan, which is a heuristic plan I proposed. Here, based on the home location, there's a set of schools around the student that are determined according to certain rules. And in the home-based plan, the number of school options is reduced. And so there's no additional priority for those living within 1 mile. And after giving this heuristic plan to the school board, as well as simulating these outcomes, my research has been focused on how can we use optimization to come up with the best menus and priorities. And this slide compares these assignment plans by simulation, not using the large market model anymore, but using a realistic model that takes into account the stochasticity in student application as well as their preferences. And here, I'll focus on the objectives, the busing requirements for the city, since for elementary school assignment, the city pays for all the school busing, as well as the expected utilities of students in various neighborhoods, and predictability as measured as the chance of getting their top choices in their set of eligible schools. Here's comparisons of the 3-zone plan and the home-based plan. And we see that the home-based plan reduces the number of choices students have, which leads to a reduced busing requirement on the city. But this also reduces their expected utilities. In a prior work, I used a simpler optimization framework to use the same miles bus per student as the home-based plan, but improve the expected utilities of students both on average as well as for those with the lowest expected utilities. Moreover, this improves the predictability. However, this previous approach could not limit the average bus coverage area, which is the area schools have to cover to pick up students, and that's undesirable. And using this improved theoretical framework as well as the new algorithms in Theorem 2, I'm finally able to account for all of these desirable objectives. So this uses less busing requirement than either 3-zone or home-based plan, while improving on the expected utilities of students, while improving the predictability as well. Let me summarize again the contributions here. So I illustrate that restricting choice may be good. I characterize DA and TDC under flexible inputs. I give efficient algorithms to compute these optimal inputs and apply the framework to data. The full paper with the code and data are available on my website. Let me conclude this talk by giving a discussion on practice-driven research. I want to make 2 points here. The first is the importance of listening and responding quickly to policymakers. So I heard about Boston's desire to reform their menus and priorities in the news in early 2012. And after that, attended many dozens of community meetings simply as an interested member of the public, where I was able to meet various parents, school board staff, as well as city committee members, in order to listen to their desires, as well as try to think of a rigorous way to consider them. And finally, in September, I had the opportunity to give a 10-minute presentation to the city committee in a meeting that solicited public feedback. And after that, I finally was able to gain an increased audience with city committee members as well as school board staff. In November, I was finally given access to micro-level data and commissioned to help the committee analyze various plans. And notice that many months of listening and dialogue simply as an outside member of the public is needed before being able to have the opportunity to collaborate closely. And in the next few months, there was a period of close collaboration, which ended when the committee made a final decision to go from the 3-zone plan to the home-based plan that I proposed. And after that, the collaboration has been on the back burner, and it's mostly me focusing on the subsequent research. So what I want to emphasize is the importance of listening, as well as the brief period in which the policymakers may want to collaborate, which oftentimes there may be a political burning platform. So it's important to respond quickly and capture the opportunity. The second point is the importance of building bridges between theory and practice. Building bridges is important because the interest of researchers is coming up with new knowledge, while the interest of practitioners is to meet current needs, including putting out fires and keeping the system running. And most current needs do not need to be resolved by coming up with new knowledge. So the intersection here can be very small, but if you're in this green region, the intersection, that could be the best practice-driven research. Because this region is so small, it's important that we need to build additional bridges. And this is what I do in this research project. First, understand the status quo. Identify policymakers wanting to do incremental changes. Then conduct simulation analysis, which leads to theoretical analysis, and finally coming up with novel methodology to do everything in a more systematic and rigorous way. And the bottleneck I find in this process is that it's difficult for new researchers to know the status quo, as well as find practitioners wanting to do incremental changes. So as a systemic solution to better facilitate such practice-driven research, it will be helpful for us as a community to make it easier for researchers to learn about the status quo, as well as connect with these change seekers. Please feel free to reach out to me by email if you have questions about any of this talk or if you want to discuss further. And I look forward to the rest of the conference.